Let me actually turn this off so that I have more of these. So I wanted to mention a few open problems, and feel free to also propose your own open problems if you have some. So the first one is easy to describe. So this relates to the entropy inequality that I mentioned. Remember that for a matroid M, so question 1. So when we wanted to basically give a counting algorithm for a matroid M, what we did was we maximized the sum of the marginal entropies. So pi log 1 over pi plus 1 minus pi log of 1 over 1 minus pi, where p1 through pn was in the convex hull of all of the indicators of bases. And the end result was that this is basically additive O of rank approximation to the number of bases. So what I didn't tell you about, so first of all, why can't you even like computationally, why can't you even compute this? It's exactly because this convex hull is separable. Okay, so linear optimization over bases of matroids we can do by the greedy algorithm, and being able to linearly optimize functions over some polytope is the same as being able to optimize convex functions over the same polytope. Okay? So you can compute this, and this is an additive O of rank approximation to the number of bases. Turns out that this also works for the intersection of two matroids. So you take your two favorite matroids, you look at the convex hull of common bases, and the same convex program, you can first solve it because, again, the intersection polytope of two matroids is also separable. And you can also prove using more sophisticated methods that this is an additive O of rank approximation, right? So to give you an idea of what you can get from intersections of two matroids, for example, you can get the number of bipartite perfect matchings in a bipartite graph. Okay? So if you have a bipartite graph and you're looking at perfect matchings, it's exactly the intersection of two matroids. So your elements are edges, so you're looking at subsets of edges. One matroid is the constraint that have degree at most 1 on top. So subsets of edges which have degree at most 1 at each vertex on the top, those form independent sets of a matroid. It's like the partition matroid. So that's M1. And for M2, you get exactly the same thing on the bottom.
So what you're computing now?
Number of perfect matchings.
For bipartite?
Yes. Right. So if you define your matroids like this, the intersection of these, or the common bases of these two matroids exactly count the number of perfect matchings, the number of perfect matchings in this bipartite graph, right? So the fact that you can do this for any two arbitrary matroids is basically a generalization of this, and it's also very much related to this van der Waals conjecture, which Leonid has also proved using real stability and so on.
So
now, yeah.
But it's additive or?
This is additive.
But is it log number of bases?
So this gives you an additive. So for bipartite matchings, gives you an additive O of n approximation to the number of perfect matchings, to the log of the number of perfect matchings.
So it's multiplicative.
Yeah.
And what constant?
Sorry, log of this. So you get e to the n. Not the best thing.
So does it correspond to this like product of this
product sum of columns times sum of rows.
Yeah, you can show that for bipartite matchings, it's exactly the same thing. But for general matroids, it's slightly more complicated.
Okay.
Yeah. So now it begs the question: if you have an arbitrary polytope over which you can optimize, right? You can still run this convex program, right? So one case which is not captured by matroids or intersections of matroids is perfect matchings in a general graph. Okay. So now let's say B is a perfect matching in a general graph. Here G is not a bipartite graph, right? So we know how to linearly optimize over this polytope using very sophisticated algorithms. And you can, using those, you can optimize this function still. Is it true that this is still an additive of an approximation to the log of the number of perfect matches? It's not?
I don't think so.
Do you have experiments showing this, or? So this is a generalization. Yeah.
Something similar.
Sorry?
I was thinking about something similar, not exactly that one. It's happened to me.
So there is actually some evidence that this might be true. So for perfect matchings in general graphs, there is this conjecture of Lavash and Plummer, which says that if so, basically the simplest way to describe it is I have these words too. So the simplest way to describe it is that if G is K regular, and I'm putting more assumptions than you need, but K edge connected, then the number of perfect matchings is something like K to the omega of n. This is true for, so let's say omega of K to the omega of n. Okay, so this is true. The conjecture is for large enough K. Okay, so this has been proved for K equals 3. That when you plug in K equals 3 here, you get at least an exponential number of perfect matchings. But the general conjecture for general K is still open. And why is this related to this fact? So it turns out that if your graph satisfies this property, being K regular and KH connected, the fractional point, 1 over K, so on, this is inside the convex hull of all perfect matchings. Okay. So if you compute the sum of the marginal entropies for this, you exactly get an inequality of that form. Okay. So that's all. So the fact that this conjecture hasn't been disproved is the only evidence I have for this being true. But yeah, so that's one open problem. Okay. So any comments, questions on this?
So actually, there is this version of this conjecture. There is another look at this conjecture, which is like van der Waals.
Yeah. This is basically a generalization of you can think of it as a generalization of van der Waals into non-quadratic graphs.
Specific class of doubly stochastic matrices, which belongs to that polytope, that Edmonds polytope.
Yeah.
And you have that regularity condition.
Yeah, you can phrase this conjecture in many different
It
ways.
would be great. Yeah. By the way, it would be the best, absolutely amazing success if it's something like this.
So in general, yeah. So anything like complete log concavity or anything coming from Hodge theory, which works with general graph perfect matchings, I think is of interest, and it might lead to proof, some sort of a proof of this conjecture.
By the way, you know what would be, Nima, what would be even less, so say, the cool thing about Log-Concave, those polynomials, that you can do the membership and support. Okay, so here's the problem. So you have a polynomial given as a black box. Okay, with some promise like that strongly Log-Concave. And you would like to check whether specific monomial, for instance, x1, x2, xn is in that is in the support.
Yeah.
And you can do it for strongly
It's
local.
because it's almost the same as the submodular base polytope, right? So it turns out to be,
Yes, you
yeah.
can use, but it requires some proofs, but yeah, you can do it. Yeah. So question is, can one reduce checking whether there exists matching in general graphs
Yeah,
to
that's-
this problem? Okay.
Yeah.
Yes.
So testing membership in this polytope is something we know how to do, but we don't know how to do with like concise linear programs or things of that sort. So it's a question of great interest in
Can
computer
you
science.
say again, what is the statement that the conjecture is having trouble?
So the statement of this conjecture is that maximize this objective over the convex hull of all perfect matchings. Okay. Then the difference between this maximum and the total number of perfect match, the log of the total number of perfect matchings is O of n. So this maximum is an upper bound on the log of the number of perfect matchings. So you have to prove basically a matching lower bound with an additive loss of O of n.
Here we're looking at all graphs.
All graphs, non-bipartite graphs. This is true for bipartite graphs. So the algorithmic implication of this is that you get basically an e to the O of n deterministic approximation. To the number of perfect matchings. Which we currently don't know how to do. There are randomized algorithms which achieve this factor, but we don't know how to do it deterministically.
The randomized algorithms that do it for general graphs?
Yes. I think Barvinok has a few results on it.
20 years ago.
1 second, but
Oh, sorry, I didn't see you.
it works for any.
Works for any, you take Gaussian random factor and then you square it. Yeah, it gives you, if you do it, there is a real version that gives you 0.28 to the n, and there is a complex version that gives you 0.56 to the n. But there is no quaternionic version, unlike for the determinant for each one.
All right. So okay, so let me mention the second open problem. So this is more of a curiosity at this point, but the question is, okay, so in Cadison-Singer and applications like Ramanujan graphs and things like that, you really care about the roots of polynomials, right? So you have these interlacing families, and you're arguing about their roots being real and the roots of the convex combinations being real. Can you do anything with log-concave polynomials to get results of that form, right? So to make it more concrete, here's a conjecture, okay? So let's say that this is some form of basically Cadison-Singer. So let's say that A1 up to AN are rank 1 matrices, such that for all I, AI is, in a PST sense, less than some epsilon 1 times the sum of all AI. All AJ. Okay? So this is like the sort of condition that you need in Cadison-Singer. Now let's say that mu is a distribution on basically subsets of size k of these n vectors, right? And mu is a CLC distribution on subsets of these. And furthermore, you have this property that probability that each element I is in some sample from this distribution is at most some epsilon 2. Okay. Then is it true that the probability that sum of AJ, J in S, is less than of epsilon 1 plus epsilon 2 times the entire sum is strictly positive. Okay. So the reason I mention this is that Sharan and I have proved this when you replace CLC by Strongly-Riley here. Okay. So the proof doesn't go through for CLC distributions because you have to still argue about the mixed characteristic polynomial, and that polynomial is basically, so you start from the generating polynomial of this and the determinantal polynomial of these, and both are real stable. You do some operations on them, you get the mixed characteristic polynomial, and you prove that it's still real rooted, right? So when this thing is CLC, the operations might not preserve real rootedness, but could it still be true that this is positive? So this is basically like you're doing Cadison-Singer with like a matroid constraint, if you will, because all you care about is that something in the support of your distribution is basically thin with respect to the whole sum.
By the way, there is one version of this Cadison-Singer question. So say you start with polynomial of homogeneous of degree 2, okay, which is strongly log-concave but not necessarily real stable.
Of degree 2?
Yes.
No, two variables.
Oh, two variables, okay.
Which is not necessarily real stable, but which means that you have Newton inequalities.
Okay.
Okay. So define now for two variables, define this mixed polynomial. And it will be real rooted. Actually, it will be real rooted for any case of two variables.
What is the mixed?
Mixed, apply those operations, this product of those 1 plus derivatives or 1 minus derivative.
Okay.
Yeah. So anyways, and you will get polynomial which will be real rooted if you have two variables. You only need non-negativity of coefficients. Okay.
Okay.
Okay. Now what is? So and now the question is about extremum case of Cadison-Singer. So you will get for all those strongly log-concave. You ask what would be the worst case where you get the worst bound on the maximal eigenvalue, and you would in a real stable case it would be linear form to the power n. In that strongly log-concave it's not true. It's not unique.
So I'm not sure if I followed, but do you wanna come here and describe it?
So the mixed polynomial again, you start with this polynomial, two variables. This is one. The mixed characteristic polynomial which corresponds to this one would be sum of the n and 2 this actually will be mixed characteristic polynomial in this specific case.
This is a univariate polynomial in X.
Yes.
Okay.
Yeah.
Wait, so in the first, what's the, so it's a sub n1 and
The coefficients of this original. Okay, so it will be a sum of those polynomials which we actually interlacing.
okay.
Yeah. So and this will be exactly mixed characteristic polynomial of this guy. So what was the formula? You take product of
1 plus partial
yes. Yeah.
v1
So if you
plus-
apply 1 plus partial derivatives and do so this is what you will
So
get.
the claim is for any bivariate log-concave
yeah.
polynomial,
Yeah, it
if you
will be-
apply those operators, it's
It
real.
will be rewarded, but it's not interesting. So now you would like to prove your bound on the maximal eigenvalue. For that you will need certain relationship between coefficients, and Newton inequalities are sufficient to prove that okay.
You mean
Now,
the same one.
But this is like a degree 2 polynomial, right? So its
no,
roots are.
this is degree 1. You start with, yes, this is degree 2. In this case, because other roots will be zeros. Okay.
But you're saying for any bivariate, any
Yes.
degree.
Yeah,
Okay,
yeah.
this-
So you will have real roots, but to get upper bound on the maximal eigenvalue, you need some extra condition. So for instance, strong long concavity will give the upper bound. Pretty much like in your paper. Actually slightly better because it's a special case. Okay? So now you ask, what is the worst polynomial which gives you that thing? That analog of your unique.
You mean which saturates the upper
Yes,
bound?
yes. Okay.
Okay.
So, and in your conjecture, it can be formulated in this way. So the worst, in general, the worst case, it's a product, it's a rank one. You don't, yes, so it's rank one polynomial, meaning that linear like this. Power of linear form.
You mean it's a bunch of derivatives of something?
Yes, yeah. Okay.
Which corresponds to all the matrices being the identity.
So anyways, in the strongly log-concave case, it's not true.
You mean the worst case?
This is, there are other, it's not unique. In the real stables, this will be unique. Okay.
And for strongly log-concave, is this only for bivariate polynomials?
Yes.
It's not true for.
I don't know how to do it.
But it might be true for any number?
Possible, again, I did not do it, something. But for two variables, and you can get, you only need struggle. And the reason is essentially Newton inequalities.
You can prove the bound only using Newton inequality?
Only Newton inequalities.
Oh.
And because here it will be, essentially will be some simple quadratic form. Yes.
Oh,
But
I
anyway.
could prove that would be very interesting to see.
Yeah, I can, because I will be here for
Okay,
a long time. But anyways, but you lose uniqueness, okay?
Uniqueness?
Yeah, because in the real stable, this guy, in order to saturate that bound, this guy is supposed to be. It's like this is kind of analogous to that van der Waals. What is the worst polynomial for van der Waals conjecture in a real stable case? Okay, so the worst polynomial, if you use capacity, will be also this one.
Oh, you're saying I see. The minimizer of that thing is,
here,
or the maximizer of that thing is not unique.
In a strongly log-concave is not unique. In the real stable is unique.
Yeah. So the maximizer of the maximum root, assuming bounds on the traces, is unique in the real root case.
Yeah. But again, it's not proved, and it will be like this one, like this is why I call rank one because it is.
Okay, that's what you mean by rank.
Yes. Yeah. So anyway, so there are some peculiarities when you do the strongly log-concave.
Yeah, it's surprising that it's even real rooted. It's not.
It's because those guys they're interlacing polynomials.
But you're saying it in general it's real rooted.
Yeah, because it this is those polynomials x times x minus n, x minus 1 times xn minus n. So here you will have interlacing of roots. And this is why you can add them to preserve. Okay. This, and you can do because they're quadratic. You just can compute discriminant. It would be like simple correlation or kind of inequality between second and first moment, something like that.
Yeah, it would be interesting to prove. I mean, are there any general statements about real roots or univariate restrictions of these log-concave polynomials?
No, because if you think of like a univariate polynomial which is completely log-concave, it can have roots in all the places, all over the places. So I've plotted, for example, the truncation of the Taylor expansion of the e to the x, which is a completely log-concave polynomial. And if you plot it out, you can see like if you go like that's if you limit the truncation degree, this is like the complex plane, the roots will be something like this.
It's Zerger curve, right?
Sorry?
1918 or something.
Oh, okay. I didn't know that. Was this studied?
By Zerger.
Okay, I see. I didn't know.
What was that result?
Well, he proved take the Taylor's polynomial degree n of e to the z.
And truncate.
Well, it's of degree n. Then plot the roots, then contract them by a factor of n. Then they converge to the curve, the absolute value of z times e to the 1 plus z equal, the absolute value of everything. The global.
The absolute value of everything, I see.
Global. equal to 1, I think. Right, and the z in the absolute doesn't exceed 1. Yeah, that's his theorem. It's in my book. Well,
Ah, this is why I remember it so well. Yeah, I don't know.
So yeah, so it seems like you get a curve which wraps around the origin, and then just by scaling, you can just map them to any place in the complex plane. So, no.
I guess, yeah, earlier anyway, you were saying that this property doesn't factorize, so it should.
But still, you can maybe talk about being above the roots. So being above the roots means that when you shift your polynomial by the corresponding point, then you're basically completely log-concave in the positive.
There is a word for those polynomials which just in one variable essentially, which is strongly log-concave. Because they're Minkowski, but there is a word for those because they're volume polynomials.
Yeah.
Any polynomial which is strongly log-concave can be realized as...
I think actually one of the exercises is saying something about the exercise 3, part 1, the part we skipped.
So you want people to prove that Shepard theorem?
No. It's not the connection to volume polynomials, but univariate polynomials are completely log-concave if and only if when you multiply the coefficients by the corresponding factorials, you get a log-concave sequence. No. Shepard's theorem is saying something stronger, that you can always represent this as a volume polynomial. Do I have time for one more?
Yeah.
So, all right. So we skipped the Hodge theory question, which is good because that would have taken half an hour. So here is one other problem. So problem 3 is, it's actually related to problem 1. Okay, so here we were doing some sort of a convex program over the convex hull of a set, right? Now you can sort of ask, what if your set is a weighted set, or you have a distribution which is not uniform over a set, right? What does that even correspond to? So it turns out that you can say something like this, that if you have mu is basically dehomogeneous, if you have G mu, which is dehomogeneous, testing membership in that convex polytope, you have to replace it by this, that you want to basically find the maximum over LS of basically a linear function multiplied by, so product of I and S of mu S. So let's say that you have an oracle which gets some positive numbers lambda I, right? And gives you the set that maximizes this. Okay, so is the oracle. So you have an oracle like this that maximizes these things for you. And for the case of matroids, this is just linear optimization over the matroid polytope. When you take the log of everything, everything becomes linear, right? So if you have such an oracle, then it implies that you can basically, then you can basically solve an equivalent form of that convex program and compute G mu at chosen point. Up to an error of basically 2 to the O of the degree. Okay. So it's a fairly natural generalization of the matroid case, right? So now why am I talking about this? So turns out that even if you have an oracle which is an approximate oracle, okay, so if you so let's say that you can't solve this problem, this maximization problem exactly, but you can solve it up to a factor of alpha. Then this alpha just goes through and you get an alpha times 2 to the O of degree approximation, right? So there is a problem for which we have some sort of an approximate oracle, and that problem is computing the volume of a zonotope. Let me erase. So if you have, so let's say that you have a bunch of convex sets, and these are all, for now, line segments. Okay. Then the volume of Z1, K1 up to Zn, Kn, this is a completely log-concave polynomial. And you can expand it out. This is basically the sum over all subsets of, if all of these are in R to the D. This is a sum over all subsets of size D of basically the absolute value of the determinant of Ki's INS times Z to the S. Okay, so these are line segments, so you can think of them as vectors. When you put D of them together, they have like a volume or a determinant. You can expand it out like this, right? So it turns out that this maximization problem, finding a maximum of these determinants, you can do approximately up to a factor of 2 to the degree, right? This is because you can maximize the square of this thing, okay, which is the maximum of a determinantal point process, right? So this is the optimization problem I showed early in the talk, okay? So this goes on, this goes through, and in the end you get an algorithm to a deterministic algorithm to basically 2 to the O of D approximate volume of K1 of the Minkowski sum of K1 through Kn, which is what's known as a zonotope, right? So question 1 is, can you generalize this to arbitrary polytopes instead of, so let's say that for simplicity, let's say that K1 through Kn are simplices. If you put a bound on the dimension of these simplices, there is a trick that gracefully that your approximation factor basically gracefully degrades with the dimension. But can you do this for full dimensional simplices? Okay. So I have no good intuition of what these coefficients here look like and whether or not you can maximize them. So why is this interesting? Okay. So that
Mixed volumes.
yes, but I don't have a good intuition for what mixed volumes of simplices look like. So let me tell you why this is interesting. Okay, so in general, when you have a convex set in R to the D and you want to compute its volume, you can either do randomization and do MC methods and compute a very good accurate estimate of it. But if you want to do deterministic algorithms, there is a very strong lower bound saying that so no deterministic algorithm can do better than D to the O of D. Okay. So this is in the model where you have just a separation oracle for your polytope, for your convex set. Okay. Now the question is, if you have a concise description of the convex set, such as like a Minkowski sum, or if you have a bunch of linear inequalities which describe a polytope, can you break this barrier and go beyond D to the D and get something like 2 to the D? Okay. So that's so this is that's why it's interesting. And like I said, zonotopes is maybe a simple case where you can already do this, but I think it would be interesting to even see this for when you have a Minkowski sum of simplices. So there is also some hope that this might also generalize. So may also work for polytopes given explicitly, meaning that, so let's say that your polytope is given as this thing. You have a bunch of inequalities describing your polytope, and you want the running time of your algorithm to be polynomial in the size of the input description. So the reason I'm saying that this whole theory might even like extend to the case of polytopes is that if you take so let's say this is a polytope P of A and B. So volume of P of A and B is a log-concave polynomial of B over some convex cone. So if you think of the polytope described by these inequalities, if you perturb the B's, you're basically moving the facets of the polytope. And there is some region in which you haven't changed the polytope combinatorially. No new vertex has appeared, no old vertex has disappeared, and so on, right? So that turns out to be a convex cone, and volume of this polynomial is a log-concave function over that cone. Okay. It's even completely log-concave when you generalize the notion of complete log-concavity from the positive ortho to cones. So it would also be very interesting to compute, or you somehow generalize this machinery to compute the volume of a polytope given by the set of linear inequalities within a factor of 2 to the d instead of d to the d.
So if you over there, so if you approximate that maximum with error, which is itself exponential, simply exponential, you also get simply exponential.
Yes. Yeah.
So,
That's
but
fine.
over there, okay, those mixed volumes, you can approximate them by
But you need
function.
randomness.
Huh?
But you need randomness.
No,
So Leonid has sorry?
mixed volumes are not known even with randomness.
Leonid has a
exponential factor.
Ah, that.
yeah.
No, but he's after exponential factor.
I'm after exponential. Yeah. But you need randomness. The whole point of this game is to avoid randomness.
So anyway, so if you have, okay, there is a case when you don't need randomness. Okay. Where already non-trivial, with those guys are zonotopes of fixed number of rays. If those guys
If the dimensions are
not
sorry.
just dimension, yes, the zonotopes which are sum of small number of
Oh
rays.
yeah.
So in that case, you don't need randomness. And the thing is, the cool thing is that stuff which approximates will be itself kind of concave.
But if what you start with is a zonotope, then the Minkowski sum of zonotopes is also a zonotope, and we already know an exponential approximation for zonotopes. The whole point of the game is to go beyond zonotopes.
So anyway, so the way would be to look for cases where you can do the deterministic. So again, if you have exponential deterministic algorithm for mixed volume, it can give.
So how do you get d to the d for this problem?
Oh yeah, d to the d is very easy. You just approximate your zonotope by an ellipsoid. So there are algorithms where you can basically produce an ellipsoid which basically when scaled by a factor of square root d, so there is an ellipsoid inside the convex set that when you scale it by a square root d becomes an ellipsoid which contains your polytope. No, so that's for symmetric. When you scale it by d, it becomes something that contains your polytope or convex set, and you just output the volume of the ellipsoid. So computing that ellipsoid, you can do it in deterministic polynomial time. And it's interesting that you can't even you can't do any better than that in the general case. So yeah, so I think that's it.
Any other comments? Okay, well, thanks. Okay, so I guess that's the end of the workshop. I hope it was kind of intense, but I hope everybody learned something and got some problems out of it. Let's just thank all the speakers again.